So previously we look at the what we call sampling rates. Sampling rates means that you can divide the x-axis. You divide the points by x-axis. So the bigger number, bigger number of sampling means you set a bigger more samples in the whole window. So more samples is better in terms of the smoothness of the signal. Okay, now because of in computer they look at the x and y axis, so that they can make easier for them to plot in the computer. So there must be some one more axis, which is the y axis. We need to make sure that the resolution of the y-axis is correct, appropriate to be used. So that's why we need to look at the amplitude resolution. The proper selection of the resolution, you can get what we call that, a smoother signal. Alright, so for this one, we need to look at the bits. I think some of us are already familiar with the bits. So with one bit, just this one, just to visualize what is bit. So if you look at here, if you have bit is 2 power of m. So m is number one here. There is should be m. 2 power of m. If one bit, 2 power of 1. What is mean by 2 power of 1? Which is we have imagine you have two lines. Lines number 1 and lines number 2. So the sample only can move at that 2 level only. Okay. So which is 1 in the middle and then number 2. So only 2 steps up and down for 2 bits. So if you have, although you have very big number of sampling rate, okay, still you can see your signal it's not very smooth. Okay, so that's why you need to have select proper resolution. So let's say we choose a higher bit, which is 2 bits. 2 bits mean 2 power of 2, which is 4. So we have 4 level. So the points, the sampling points, can move at that 4 level. Okay, so if you look at it, you see that is better representation. The blue line, the light blue line, is the original signal. Okay, suppose that we need to see that signal, something like that. Okay, so you should suppose that it be like this. It's a good signal, original signal, but we only have 4 bits, so 4 lines. So that's why it likes like this. So of course, if you choose more resolutions, for example, if you choose 3 bits, so then we can see more level, 1, 2, 3 up to 8, because of 2 power of 3. 2 power of 3 means 8. So now signal becomes smoother and better. And of course, if you choose 4 bits, now the signal become better. And so if you look at the notes down there, a 16-bit ADC will discretize the amplitude range of signal to the resolution of 65,536 lines for 16 bits. So the signal will be much better, smoother. You can represent the original signal better. So that's why when you want to purchase, when you want to buy DAQ, data acquisition system, you must look at the resolution of the DAQ. Make sure if you want to measure the fast signal, make sure that you choose a better resolution for your DAQ. Otherwise, it will show bad signal, bad shape of signal. Although you have a very huge, very high sampling rates, still you cannot get a good signal. So this is very important of the resolution. Remember, the sampling rates deal with the x-axis, resolution deal with the y-axis. So a little bit more about the this is actually what we're talking about, the DAQ, still in the DAQ part. So what is dynamic range? Dynamic range is the ratio between the largest and smallest signal that we can analyze at the same time. So for example, the lowest signal is 10 Hz. We can measure 10 Hz, and the DAQ also can measure at maximum, for example, 10 kHz, which is 10,000 Hz. So that's a range of measurement from 10 Hz up to 10 kHz. For example, this is just an example. The more the range is better, but it's more expensive. Okay. Also, the dynamic range is affected by a few components. If you can look at the notes here, it's affected by the ADC resolutions, the one that we looked just now. So more resolution, better in terms of dynamic range, and then the amplifier. In the DAQ also we have amplifier. So how much the amplifier can amplify the signal better than the noise floor, because of course electronics component, they always have a noise. So the DAQ must amplify a little bit to make sure that it's higher than the noise. That we call a signal to noise ratio, SNR. We will look at this SNR after this. That's in the notes. Signal to noise ratio. So basically, all DAQ have this function, SNR. If you purchase DAQ, you look at the spec, especially on National Instrument. I think next week I'm gonna bring the National Instrument, not here, but in my lab. I think I'm gonna bring you to my lab. So I'm gonna give you the DAQ. You're gonna look at the DAQ. What's the specifications that written on the DAQ? For example, they have a resolution. They have SNR. How much the signal to noise ratio in terms of dB, decibel. And then there is anti-aliasing filter performance. How much the performance of the filter? I think we have looked at the aliasing. Dah tengok dah anti-aliasing. And then DSP performance, digital signal processing performance. I think that one is the hardware. So dynamic range, it depends on this four inputs. Okay. Oh, I think we didn't go the anti-aliasing. Okay, now we go to anti-aliasing. What is aliasing? Alias mean a signal comes in, but it appears that, for example, we measure 10 Hz signal, but because of the aliasing, the 10 Hz signal appears as different frequency. So that's it, aliasing. So the thing is, this phenomenon appears when we have a high frequency component. It comes into our system, but our system shows a low frequency. So it's aliasing. So it's very, very misleading to our system, especially in our car, because in the car there is sensors who measure all the signals, but if it wrongly measures signals, it will give a wrong information to the car. That's why we need to make sure this aliasing is not happen to our system, because the car always measuring a dynamic signal. So it's always happening at the A to D hardware. So if you look at, you must look it properly. This one, for those who familiar with this one, tak apalah, saya nak tunjuk je lah. So if you look at let's say you have a maximum frequency. For example, here you have maximum frequency. I wrote here. So for this one, sorry, wrongly select. So if you look at the signal, 1 second here, this is 1 second. Okay, so how many cycle that we have as an input? We have, I change the color, blue color. So 1, 2, 3, 2. Okay, 2 cycle. We have 2 cycle per second, which is the frequency will be 2 Hz. 2 Hz input. But the sampling rate that we choose is, for example, we choose 2/3 Hz. Okay, 2/3 Hz, which means 2.666 kan? 2.666 Hz. It is the same value as the maximum frequency, but a little bit more than maximum frequency. So the ratio between the sampling frequency and the frequency is about 1/3. The ratio between sampling rate. So then in 1 second, this is 1 second line. Sorry, this is 1 second line. 1 second line. So in 1 second line there is how many points? 1, 2, 2 something lah, 2.7 kan? 2.6. So only 2 points appear in the 1 second, but after that we have another point lah. So if the computer see this one, the computer will see like something like this. So one cycle in computer, the computer see not a complete cycle in 1 second. So this is what we call misleading, aliasing. The signal comes in 2 Hz, but the computer see not even 1 cycle. See? So the computer shows a misleading information to us because of we choose sampling like that, 2.666 Hz. So let's say we increase the sampling rate. We increase sampling, let's say sampling frequency we choose 3. Still it's close to the maximum frequency, 2 to 3. So the ratio is 1.5. The ratio between sampling and frequency maximum is 1.5. So look at the signal. If you look at the signal, so one here, and one here. Three sample in 1 second. So there's another sample here after 1 second. So if you computer plot this one, it shows something like this. So still it's not complete 1 cycle. The computer will show us. So still misleading. So how about if we change 2 times of the sampling frequency? We choose 2 times of the original frequency. So we have 1, 2, 3, 4. We have another one here. Okay, this one means 4 points in 1 second. So this is 1 second line. So 1, 2, 3, 4. Okay. Why I didn't choose this one? This is sample number 0. The first sample always we call it sample number 0. Okay. This is sample number 0, sample number 1, number 2, number 3, number 4. So 4 sample in 1 second. So if you plot again, it looks like straight line. So if you choose a sampling rate same as the maximum frequency, the maximum frequency is not appeared, it's only appeared as a straight line. So also it's a misleading. Then let's say we choose more than 2 times. For this example, it shows 3 times of the sampling frequency. Maximum frequency. So 3 times, then we have 3 times maximum frequency 6 Hz. So 6 points in 1 second. So this is 1 second line. So number 0, 1, 2, 3, 4, 5, and 6. So 6 sample in 1 second. So if you computer plot again, although it's, when you plot, it plot like that, sharp edges, it doesn't plot the smooth line. The computer only see a dots line only. So it just connect each lines with a straight line lah. They don't know the curve line. So if you plot again, and then okay, it shows a correct frequency. It shows a correct frequency, which is 2 Hz. There's 2 lines that the computer show to us, but still we have error because of it's actually sharp edges. It's a sharp line, I think I shown in the Daisy Lab how when we set improper sampling, it shows like sharp lines, not a proper line. Dah tunjuk ke? Kalau tunjuk saya tunjuk lagi. So okay, so now we come to conclusion that the sampling rate must be, in order for us to see the correct frequency, we need to choose more than double the maximum frequency. If we choose maximum frequency, if we predict the maximum frequency is 10 Hz, so sampling rate must be more than double. Not double, kalau double very, it will give a straight line. So not double, but more than double. For example, it's my voice here. My voice is I don't know how much the frequency of my voice, but maybe usually the audible sounds is 20 Hz to 20 kilohertz. That's the audible sound that we can hear. But the voice of human voice, I think probably 5,000 Hz. So let's say the maximum frequency of our voice is 5,000 Hz. So how much the sampling frequency that we want to set to the DAQ? So it must be double or more, which is, so the maximum frequency is 5,000 Hz. So we choose 10,001. So sampling rate must be 10,001 at least. Okay, so that it can capture that 5,000 Hz. Okay, more than 5,000 Hz. Let's say we set 10,001 as a sampling rate. So our system can measure up to 5,000. Let's say 6,000 frequency comes in. What happened to the system? What happened to the signal? It's showing the lower frequency, isn't it? The 6,000. Let's say we set 5,000. We know 5,000 Hz. And then we because we know the maximum frequency is 5,000 Hz, we purchase DAQ, which is 10,000, 11,000 lah senang. Kan? 10,001 ni just extreme example. Let's say my voice is 5,000 Hz, and then I purchase DAQ with 11,000. We set 11,000 sampling rate, the maximum. Suddenly there is some voice, another voice who is 6,000 Hz comes in. So what happened to the voice? What happened to the frequency? Our system will show a lower frequency of that one. Okay, not 6,000. Maybe it appears, I know you have to do calculation, maybe it appears as a 1,000 Hz frequency. Although the original one is 6,000. But because we failed to set a correct sampling rate, it will appear as a low frequency. How to solve this one? Because we already purchased the sampling rate, the DAQ. It gives us 11,000 signal. So how to solve that one? Buy new one. Of course, the easiest one, buy new one lah. But we set the filter. Our intention is to make sure that the system showing the correct information. That's the most important. Okay, this is concept. If you fail to measure, it's okay, but it's better you fail to measure than you measure the wrong information. Okay? Understand? You measure the wrong information is bad because it will give the wrong action. But if you cannot measure, it's okay. You can measure, it's okay. You cannot measure, it's okay. It doesn't give it also give a bad action after that, but it's better than you measure something and having the bad incorrect information. So what we do is we filter the 6,000. we make sure that 6,000 hertz not come into our system. We filter it out. We only let up to 5,000 hertz only. Okay? So 6,000 for those who actually come with a voice 6,000 hertz is not captured by our system. Okay, that's the only solution. So that one we call anti-aliasing filter. Anti-aliasing filter. Oh, this is in the slide. There is another example, just to show this importance of how to select proper sampling. Okay. This one is just I mentioned just now. The sampling must be twice, 2 times and above. We call it as a Nyquist theory. I think this is a France people and the name Nyquist. I don't know. Mr. Nyquist have proposed there's a theorem. The sampling must be at least 2 times, not 2 times, more than 2 times. Okay, kalau 2 times nanti dia hilang, dia just flat. But from my experience, not 2 times, but it's 10 times. 10 times. 10 times you still can show the smooth signal. Smooth signal. Okay lah. 10 times the maximum frequency. So like just now I showed the example 5,000 voice. You get 11,000 sampling rate. I think for Nyquist theorem, yes, you can do that one. But if from my experience, you need to have a 10 times, which is if you measure 5,000, please get up to 50,000 and above sampling rate. Otherwise, the signal not giving a smooth output. Of course, the larger is better lah. Tapi it will get you will sacrifice the storage because more samples. Imagine, remember, more samples, more storage. Okay, so this is actually what we're talking about. It's an anti-aliasing filter. So we need to introduce the anti-aliasing filter. Every DAQ actually has its own anti-aliasing filter. So whenever we set the sampling at that amount, it will set automatically. It will set the anti-aliasing filter. So make sure that more than that setting by us, it will not comes to the system. It will be automatically filtered. So that's actually a anti-aliasing filter. Actually, basically, anti-aliasing is low pass filter. Okay, the term low pass. What you can? I think some people will get confused with this one along the way. Up to end of the subject, they will confuse with the low pass. Low pass means only low frequency can pass the filter. Low pass. Not filter the low frequency. No. It only allow low frequency, low pass frequency. High pass only allow high frequency. High pass. So for this one is only allow low frequency. Remember, my example, if you have maximum 5,000, 6,000 we filter out. So all the high frequency we filter only allow the lower than 5,000 hertz. So this require. That's why anti-aliasing filter is a low pass filter. It's a low pass filter. Okay, tapi if you look in the system, because we're dealing with hypothetically, theoretically, it will sharply filtered at that how much that we set the sampling, but practically it have a leakage. There is a leakage. Okay, there's a leakage. There's some filter, some frequency still appear in the system. That's why we need to set a little bit more, because theoretically it's not the same as a practical. Okay. So the rest I will let you to look at the notes. So a little bit further, I want to finish up about the DAQ. About the DAQ, is the A to D function. Actually, it's a hardware system A to D. Because of the digitalization process, remember the original signal is smooth, very nicely smooth signal, but with the digitalization process, it convert that signal, that smooth line signal, into samples. So converting to the samples, it will create errors. So analog to digital convert. When we convert signal, continuous signal, into digital, it will create sometimes, if we not properly select the numbers of sample, it will inaccurately showing the lines. So how can we calculate the errors? I introduce you the what we call mana sini tak ada ni, quantization error. It's an error specifically because of we do conversion analog to digital. So we have quantization error Q, which is EFSR over 2 power of m. Remember, 2 power of m is the resolution, m is the bits. So EFSR is the range of input. E means energy. I mean, usually we refer to the voltage. So FSR, remember, full scale range. So E, voltage range. Again, in the DAQ, when we purchase the DAQ, there is actually written in the DAQ the voltage range that can be measured by the DAQ. Usually plus minus 10 volts or plus minus 5 volts. It depends on the DAQ. For the one that we have in our lab, plus minus 10 volts. So that above than that, either it will be filtered out or it will give incorrect information. So EFSR, the maximum range. So of course voltage is the amplitude lah, amplitude. So plus minus mean 20 volts, 20 volts of range over the 2 power of m. M is the bit number. So Q is depend on the how much the range and the resolution. The more resolution means it will reduce the quantization error. So to reduce the error, I mean the possibility of error, make sure you choose a correct resolution and also correct range. Correct range. Okay. So if we choose let's say 16 bits, so the range should be smaller lah, kan? Range should be smaller so that you can get less error. Okay. So what happen if you measure the signal more than the input range, the voltage range? I'll show the some simulation, not simulation lah, drawing lah. Okay, say I think I've done it before. This is actually the okay. Look at this one. This is actually a line. This is a line for 10 volts. Minus 10 volt, and this is plus 10 volt. Let's say the input is higher than that range, for example 11 volts. What happens is it just turn into straight line. It cannot show more than that. So the signal will be like a saturated signal over here. Okay, saturated signal. So it will show the incorrect representation of the signal if you measure larger than the range. Okay, so that one is saturated error. Sometimes some DAQ will be broken because it receive a higher voltage. Sometimes the electronics will be you cannot deal with the high voltage, so it will be burned. So make sure that we look at the DAQ properly, look at the specification. So look at this, we have a quantization error, saturation error, and conversion error. Conversion error is the conversion between, if you have a physical quantity conversion. For example, accelerometer, you have a G, you have a conversion between G to voltage. So if you inaccurately select sensitivity value, it will give a conversion error. But all these three errors is very important for you to see, to choose, to make sure that you have a proper selection of DAQ. Alright, so we finished about the DAQ. I think this one, sorry, conteng lah pula. This is just a representation of how it looks like. The errors. This one, SNR. I mentioned just now about the signal to noise ratio. This is the equation. Signal to noise ratio in terms of dB, decibel. So 20 log to M. 2M is a bit number. So the more bit number, so it's better lah, kan? So better SNR. So it's very important to have a good bit number. First, you can reduce the quantization error. The other one is you can increase the SNR, signal to noise ratio, which is the signal compared to the noise floor, electrical noise. Alright, habis. Finish with the A to D. Ni contoh yang kita ada lah. So we have something like this, National Instrument. I think National Instrument did a good job. They have come up with a good products for education. Okay. Some DAQ cannot be customized, but NI can be customized for education and for application purpose. Even I use for consultation, I use NI National Instrument. It's robust and it can be customized. I think in the research, I think most of the university, all over the world, they use National Instrument. In US, of course, US, they use National Instrument lah. I don't know in German, I don't know what DAQ they use, but in Malaysia, most of the university use the National Instrument. The level of customization is very good. I don't want to promote this. I'm not really the promoter for this one. I didn't get any commission for National Instrument, but I need to put this one in the slide lah. Hopefully, if I publish in YouTube, National Instrument will contact me and give me some commission. Okay, now I have another half an hour. We actually I already demonstrate about the Z-Lab in the computer online class. Basically, if you look at my YouTube channel, I already show some basic about the Z-Lab, how to set the Z-Lab. But the most important is the practical side. Okay, how can you connect everything with the Z-Lab, and how much time for you to play with the hardware, connect the DAQ to the Z-Lab and the sensors. Okay. After this class, maybe next week, we're gonna look at the sensors, the detail of the sensors, the mechanics of the sensors, the equation that involved in the sensors. But for before we go to that one, we need to ready with the DAQ, the information on the DAQ and the software. Okay. Okay, kita tengok ah. So dari Z-Lab ni, I think in the signal processing, the two things is very important, which is filtering, and the other one is frequency domain signal. How much that we can, how can we convert the signal into frequency domain, and how can we extract information. And the rest is just visual looks. The one that you see in the software, measurement software, is only a visual looks. How can you customize everything? So I'm gonna touch on the here with the, sorry, saya kena buka mouse. Sorry, saya cari mouse juga. Okay. Sebelum before I go further, anyone have problem downloading the DAQ, installing the DAQ? Any problem? No problem, eh? Okay lah, biasa main. UMPN have usually they have experience dealing with the DAQ. Okay, but the problem with this, the problem with them is they don't know the function, how to manipulate the modules to come up with a good system. Okay, so for the control, okay, if you want to see the recording, you want to practice, go and look at the recordings. So for the generator, we can set the apa nama panggil input lah. But for that one, you refer to the my YouTube channel. You can set the input to the generator. I will use generator because of generator give us theoretical wave. If I choose sound card, it will give a random signal. So I choose without modulation. Let's say I choose more than one, three signal generator with a 3 different signal. So this one I choose sine. This one remember 10 Hz. This one amplitude 4. This one I choose a sine wave. I increase the frequency up to 100, and the amplitude I change to 2 Hz. Okay, so generator 3, I choose say 200 Hz sine wave. This one 3 Hz. Okay, so always if you deal with the, because you're not your subject, your scope of subject is not with the DAQ. Okay, not DAQ. DAQ is just a tool for us to understand the measurement concept. But if you know DAQ, it's quite interesting. So let's say I set 3 generator. The other one I name it as a Gen 1. Okay, with 10 Hz signal and amplitude 4. Okay, this generator, okay, remember the first thing that we learned in the class, about the DAQ, is the sampling and block size, kan? So when we create a signal, we must also set the sampling rate and block size. Sampling rates deals with the number of samples, and the block size deal with the size of the window. So how can we set that one? We need to go to the time bases. What kind of time base that we want to use? I double click here. So either the computer will ask us to, either we want to use a driver. Driver is the setting for the sound card, or you want to use your own setting with DAQ. Let's say I don't want to use a setting for sound card. I use DAQ. So time base, I use a DAQ time base. Okay. So I click OK. But When I click OK, I need to change the Dezilab lah. So I go to measurement, I go to the time basis, I reconfigure the Dezilab sampling rate and block size setting. So if you look at here, there's two tabs here. One tab Dezilab and one tab for driver. Again, driver is for sound card. I don't want to touch on that. I fix with the Dezilab. So now Dezilab says sampling rate is 10 Hz. Remember how much frequency that we want to generate? Is a 10 Hz signal kan? So sampling cannot be 10 Hz. It must be more than that, more than double. So 21. According to Nyquist's theory, 21 is okay, but it will show not really good signal. Let us see. So block size, you know, in one window, only one block, one number of samples shows. So it doesn't give anything, isn't it? You cannot see anything. So at least you show the 21 lah, 21 sample lah, so that you can get the whole sample, 21 sample. But for me, I choose automatic. Automatic. Never mind, we can see after this. So, and then the rest I do the same. Okay, I choose Dezilab, and then OK, and then this one OK. Choose a Dezilab. Remember, the Dezilab setting is 21 Hz, but this one is 200 Hz, and the other one is 100 Hz. So basically, generator 2, Gen 2 and Gen 3, we have problem. It will have problem of apa dia? Aliasing. Yeah? Gen 1 is okay. Gen 2 and Gen 3 we get problem, anti-aliasing problem. So let's see how can we show the signal. Go to display, YT chart lah. YT chart mean Y amplitude over T time. So if you want to show time domain signal, pick up the YT chart. Just bring it in the worksheet and then just connect. Connect. Either you make it close or just I delete this one. I right click again. You can connect by using left click. Left click here and left click here, so you can connect. So there's two ways to connect between two modules. Either you make it closer or just using left click. So when you drag in the window, of course it will create this is actually a display. We have 3 display, but it's not appears anywhere here. It's actually appear as a minimize window. So you must maximize, make sure it shows. So that we have I click this button, restore all windows. So it will show all the windows about the graph. So we have a 1, 2, 3 graph. Now because we have a huge number of graph, usually I name it. So that I get not confused. So I name it first. So this one I double click, I name it to graph 1 for Gen 1, and then auto scale, and then this one graph 2 auto scale, and this one graph 3 and auto scale. Alright, so now all good to go. And then restore all windows. It appear the windows. Susun balik bagi cantik sikit. Okay, make sure it's a good, nice looking. I don't want to block the tab, the button here. This button is very important. Button hub here very important. I don't want to block with the graph, so I make it smaller. So I run. See, one of the channel is undersampled. You know which one? The Gen 2 and Gen 3. They are undersampled. But I just click OK. Okay. So okay, sorry. Okay. So look at the first graph. The first graph is the Gen 1. It actually appears as good frequency, but it's not so good shape. How can we, you know, the Gen 1 is 10 Hz, isn't it? So how can we verify it's 10 Hz? I click here. This is actually a freeze pane. Freeze. Okay, I freeze. Sorry, unfreeze. Okay, sorry. Okay. Oh, cannot get. Okay. Apalah. Sini. So I go to the here. Sorry, not on this one. Survey. I click here. So there's two lines here. I put line here to this one and put line to this one. This peak. So let's see the this frequency. Now it's showing 10.5 Hz. So basically it's okay lah, 10 Hz lah, but it's not quite accurate, but it's still giving the 10 Hz signal. Okay, 10 Hz signal. Compared to others, we freeze this one. So if I can use survey, so peak to peak, this peak, and then where's another peak? I cannot see another peak, but whenever I choose all this sample here, this is a sample. One sample here, one sample here. Okay, so one sample here, one sample here, one sample. See, the sample is very low number, so it's not good representation of the signal. So I already made the point. So the point is you must have a good sample. So let's say, so this 3 generator, what's the maximum frequency? Which one the maximum? The gen number? No, gen 1 10 Hz. Gen 3 is it? No, gen 3 200 Hz. Gen 2 is, let me check. Gen 2 100, sorry. Itulah Gen 3. Maafkan saya asal kesilapan saya. So Gen 3 200 Hz. So 200 Hz is a maximum in this system. We have 3 frequency. So these 3 input use the same sampling rate. So the maximum that we have is the Gen 3. So I must change the measurement. If I use 200, I choose not 200, I can use 200, I can use maybe 250. So block size I choose automatic, or you can use the same number as sampling rate. Okay. Alright, so when I restore our Windows, look at the graph again. See under sample? Why under sample? Oh, sorry. Why under sample? Because of number 3, Gen 3 is 200 Hz. So I choose 400, isn't it? 400. Okay. Sorry. So stop. Time basis or setting 400, 500 lah. 500. So block size, I choose the same number, 500. Okay. So I run. So this one. So the first one is 10 Hz. Gen 1, 10 Hz. Look at the ratio between sampling rate and the frequency. The frequency is 10 Hz. The sampling I choose is 500. So what's the ratio? It's about 550, isn't it? 50 ratio. So now we see a very small signal. But the rest I need to zoom in first to see. See, this one is ratio 500 to 100. This is a 100 Hertz. So 500 is 5 times. 5. So see 5 times, still it shows a good signal. If we check the frequency, you see peak to peak, peak to peak. See, it's showing the 100 Hertz. Still showing the correct value, 100 Hertz, but the shape is not really good. Okay, and then of course if you look at this one, there I zoom in. It's not, of course Tapi kalau if we check the signal, peak to peak signal, I believe it shows the correct one. No, tak kena juga. Tak kena. It show 166. Kita punya signal is 200, isn't it? So although it's double, but still showing incorrect information. So that's why I said Nyquist theorem is just a theory. And practically, you need to use either 10 times, 5 times. You see, 5 times, still not good. Okay, but 10 times. Okay. Okay. So just final. I just change time basis to 200. 10 times 2000 to 2000. Okay, and then of course if you run, everything looking good. See, all looks good. All looks very good. This is the maximum one. So thank you very much. My recording also already finished. So I think I need to finish our session for today. See you on Tuesday next week. Okay, thank you very much. Oh, the exam paper, you want it now? The test script, your script. Follow me to my room. Okay, thank you very much. Assalamualaikum.